again, we're here to talk about section 7.6 and 7.8, which has to do with the use of dimensionless groups and also some well-known and well-studied dimensionless groups that tend to come up over and over again in fluid mechanics as being very important to the study of similarity. So the last vodcast was very long. Number 21 was about an hour or maybe a few minutes longer than an hour long. So this is going to be relatively short. Because we don't have a lot more math to do. What we have to do is an application of what we've already done in Vodcast number 21. So what I'd like to talk first about is in section 7.6, there is a table, this is on page 403, of some common variables and dimensionless groups in fluid mechanics. And these are groups that we commonly need to find similarity between different groups in order to model a fluid flow properly. Similarity between dimensionless groups I wouldn't say assures, but I guess I would say suggests good modeling characteristics. All right, so one of the numbers that we've already talked about is the first one listed in this table, which is the Reynolds number. And really, the Reynolds number is a really big deal when it comes to fluid flow. As you see, it tells you each one of these groups is dimensionless. The Reynolds number, rho VL over mu, or some sort of a characteristic length, depending on the type of flow, is the inertial forces over the viscous forces. And basically what that tells us is whether the inertia overcomes the viscosity or not, or another way to think about this is if the flow is laminar or turbulent. So if everything behaves well, it'll tend to have a low Reynolds number. If it tends to behave in a more turbulent or unpredictable fashion, the number will get quite a bit higher. Now, this is a number that very often when you see an airplane, a prototype, not even a prototype, but a model in a wind tunnel, the model will not look all that similar to the plane itself. And this is the case of the picture that I've put on our Moodle page. You'll see that we sort of have a distorted airplane prior to its being tested in a wind tunnel. The reason is because we need to have the similarity of a Reynolds number, and in order to get that to happen, it's going to look geometrically a little different. So I put that picture up specifically because I wanted you to see that and to be able to, I'll put it up right now so that you can take a look at it, so that you could see that it's not just geometry that is important when it comes to modeling. All right, so here's the airplane that I'm talking about. And you see it has this long extended nose, sort of a square thing up here, and the proportions are just slightly off, or maybe even quite a bit off, based on modeling for these variables of similitude. All right, the next number is called the Frood number, and Frood number, it rhymes with food, talks about the inertial forces over the gravitational forces. And this has to do with flow with a free surface. So if you have water moving through a ditch, for example, the Frood number is an important characteristic that needs to be similar in order to have a similarity in terms of modeling. The Euler number talks about pressure over inertia forces, and there's an important variation of the Euler number, which is called the cavitation number. And the cavitation number is required if we have a situation. Cavitation is, for example, if you've ever had a boat, sometimes the propellers on a boat will get all pitted up. It has to do with if you reduce the pressure below the vapor pressure, that you have a release of energy when the bubbles burst. And that can cause scarring on a propeller. There's a lot of other cases where cavitation, the energy associated with cavitation becomes very important. Another one that's a little bit more esoteric, I guess, there was a paper written a few years ago that suggested that cold fusion could actually be achieved inside of a bubble, and that the energy to propel it, rather than a nuclear explosion, could come from the cavitation of certain kinds of bubbles. It was never really proven, and the records looked like they were a little falsified, and it was kind of bad science all the way around. But just kind of giving you another little bit of an idea about what cavitation is. Release of energy from the burst of a bubble. Cavitation number has to do with a flow where the compressibility is important, and this is a modulus, it's a compressibility force, a modulus thing that we'll talk about later on. Mach number, we've already discussed that. That has to do, the compressibility of the fluid is important here. The Mach number, of course, is important. What it really tells you is if you're at Mach 1, that means that whatever's flying through the air at that point, or through a fluid or whatever, would be traveling at the speed of sound. There are some changes with the pressure-velocity relationships below and above the speed of sound, below and above Mach 1. So this becomes important for design. Aircraft that were designed to exceed the speed of sound had to take this into consideration and actually design the tail section of the airplanes differently in order to be able to sustain speeds, or to actually not sustain, but to be able to fly the airplane, control the airplane at velocities higher than Mach 1. Then we also have the Struhal number and the Weber number. So these are just a table of numbers that you will, at different times, hear about, and that you will also be able to consider when you are modeling something in terms of fluid flows, and it will have different properties than just the geometry. All right, so we go through this little discussion of different types of numbers and what they mean. And then one of the things that I really want to point out is when we talk about the Euler number, on the top of page 405, they talk about this other number, which I'm not really sure why they haven't chosen to put this in the table, because the cavitation number is fairly important in many, many situations. But the dimensionless group, PR minus PV, divided by 1/2 rho v squared, which is, as you can check, this would be a dimensionless group. This cavitation number becomes very important in a lot of cases. But I guess the reason, most likely the reason that they don't introduce it in the table is it really is a derivative of the Euler number. So, but we're not going to do the derivation, so we're just going to use it as it sits. All right, so these are some of the ideas that we need to consider when we're talking about modeling different types of fluid flows. And once again, deciding what variables are important, what dimensionless groups are important, is a matter of some degree of engineering experience. So at this point, we're not going to really say which ones are important or how are you going to determine that. We're going to present it to you. And when I talk about we, I'm talking about the authors and me. So when you do your homework, when you do your exams, this information will be given to you. You just need to be able to develop the similitude and to understand what that means. And then later on in your careers or in your education, you'll see situations where you'll need to develop that degree of sophistication. So, having said that, let's take a look at the problem that I'd like to do for you for this particular section, and that problem is 746. So in your textbooks, let's take a look at the back of the book, and 746 is down here on page, let's see where we are, 437. All right, so 746 reads like this. I just skipped. Okay, let me expand this a little bit so you can see it if you don't have your book right in front of you. Okay. For a certain model study involving a 1 to 5 scale model, it is known that Frood number similarity must be maintained. Okay, so our Froud number must be similar. The possibility of cavitation is also to be investigated, and it's assumed that the cavitation number must be the same for model and prototype. All right. So it says then that the prototype fluid has some properties. Basically, it's water at 30 degrees centigrade, and the model fluid is still water, which is good, at 70 degrees centigrade. If the prototype operates at an ambient of 101 kPa absolute, what's the required ambient for the model? All right, so if we take a look at the parameters of this problem, this is basically what we're looking at. We have a prototype where we're going to be looking at the model or the prototype in water at 30 degrees and a pressure of 101 kPa. We want to maintain Froude and cavitation number similarities for water at 70 degrees. We want to know what the pressure is going to have to be. All right, so first of all, what is the Froud number? The Froud number is, from our table, V sub m, well, this is for the model, divided by the square root of G sub m over L sub m. And to maintain similarity, what that really means is that those have to be the same for prototype and model. Similarly, well, what do we know? First of all, G is just G, right? We're not changing G force. So what we know then to maintain our Froud number, all right, C sub n down here, since these are going to be the same, that the velocity of the model over the square root of the length of the model is equal to the velocity of the prototype or of the real deal divided by L. So if this is the case, this is what needs to happen in order to maintain Froud number similarity. So that's our first condition. Okay, what's our second condition? Well, we have to maintain the cavitation number similarity as well. So basically, if we go back to page 403, excuse me, this is on page 405, what we'll see is that the parameters or the equation for that cavitation number look like this. Okay, so if we take those for the model and we look at them for the prototype, or the other way around, that we're going to have something that looks like this. Okay, so this is what we need. This is our second condition in order to maintain cavitation number similarity. Okay. So we have two conditions, and what we're really looking at is we have an absolute pressure, we also have a temperature, and based on that temperature we want to know what our new absolute pressure has to be in order to maintain that similarity. All right, so if we take this, let's just call this equation 1, all right, and we'll go ahead and just call this equation 2. If we incorporate equation 1 for velocity into equation 2, if we do a little algebra, and I'm doing this really a little quickly because I don't want to keep you here as long as I did last time, we can say then that on this side, P sub r minus P sub v of the model is going to equal rho m over rho times Vm squared over V squared times PR minus PV. All right. And we could reduce a little bit further, substituting our lengths based on this relationship. All right. So now we have some density issues, right? And we know that the density of the model, which is at 70 degrees centigrade for water, is 977.8 kilograms per meters cubed. And that the vapor pressure at those conditions is 6 10 to the 4th Newton per meter squared. Okay? And at 30 degrees, going to the table, this would be table B2 in your textbook. We find that rho is going to be 995.7 kilogram per meter cubed, and that PV is 4.243 times 10 to the 3rd Newton per meter squared. And both of these are in absolute units. So we can solve then for PRM. It's going to be the ratio of those pressures. And those units are the same, so we don't have to write them out again. Times, we're told that the size, the length, is a 1 to 5 model, right? So 1 over 5. And then we have the difference of our pressures. That will be in newtons per meter squared. This is dimensionless, this is dimensionless. And then we need to add, because I'm solving for PRM, I need to add to that the vapor pressure of the model. My units are all the same. So I should say, I didn't really ever write this out, but we could say this, let me just write this out for you. PR then is equal to rho m over rho times LM over L times the quantity PR minus PV, and then I have to add to that the PV of the model. Okay. So if I run through these numbers, dimensionless, divide by 5, a difference in Newton per meter squared, add to that Newton per meter squared, that value turns out to be 50.2 times 10 to the 3rd Newton per meter squared. You can run those numbers, and that 10 to the 3rd Newton per meter squared is kPa. So what that means is we started with a pressure of 101 kPa, which is essentially atmospheric pressure. So that means we have to drop our pressure to approximately half an atmosphere, don't we, in order to maintain Frood number similarity and to examine for cavitation. So therefore, we must drop our pressure from 101 kPa, which is essentially atmospheric, to 50.2 kPa, which is approximately 1/2 atmospheric pressure, in order to maintain Frood number and cavitation number similarity. All right, so as you can see, section 7.6 and 7.8 really just apply the ideas that we've had and then take into account some of the dimensionless groups that are commonly found in fluid dynamics. So that's it for Chapter 7. We'll see you next time for Chapter 8.